All right, so the last section that we didn't get to in Calc AB is L'Hopitals. It's section 8.1. It's not necessary for you to know L'Hopitals in order to be successful in the AP exam, but it is handy to know L'Hopitals and when you're evaluating limits. You can still do the limits the other way, but this is kind of a shortcut. So if you had the limit of like 3x plus 5 over 7x minus 1. That's not very focused. There. As x goes to infinity, we know that it's going to be 3/7. Just even back to pre-calc where you find if the degree and top and bottom are the same, then it's just the ratio of the coefficients, so it's 3/7. It's also the horizontal asymptote, y equals 3/7. So this would not be an example that you would want to use L'Hopitals, but I'm just going to use it to demonstrate how you do L'Hopitals. So a couple criteria for L'Hopitals. The expression has to be in indeterminate form, and there's a bunch of different indeterminate forms. If we have 0 over 0, or if I have infinity over infinity, which one this one actually is, because if I plug infinity in, I get infinity over infinity. So this is indeterminate, meaning we don't know what the outcome is going to be. It could also be infinity times 0, or it could be infinity minus infinity. If you get infinity minus infinity, you're going to end up having to combine both terms and then evaluate it. I'm not even going to show you an example of that. There is one in the book. So I'm not going to go through all of the different types, 1, 2, 7 indeterminate forms. Most of them I think are in the book, but I'm just going to show you a couple different forms of this, and just you can apply it as long as it's in indeterminate form and the expression is written as a fraction or it's rational, which this one is. So if it's indeterminate form and it's written as a rational expression, then you can apply it. What L'Hopitals is you could find the derivative of the top and the derivative of the bottom, and the limit is still going to be the same. So this is a fraction in indeterminate form, so we can apply L'Hopitals. We're not using the quotient rule. We're not doing the derivative of the whole thing. We're just doing the derivative of the top, which is 3, and the derivative of the bottom, which is 7. It's no longer an indeterminate form. In fact, it just gives us our answer, 3/7. Another thing, if you have, x approaches infinity. Let's say I have 4x squared minus 10x over 5x squared plus 6. X approaches infinity. It is infinity over infinity, indeterminate form. And it's written as a fraction, so we can apply L'Hopitals. We get 8x minus 10 over 10x. All right, so if I plug infinity in right now, I get infinity over infinity, so it's still in indeterminate form. Okay, so you can apply it another time. As long as it's in indeterminate form, you can keep applying L'Hopitals. I get 8 over 10. Notice this is not an indeterminate form. Don't do the derivative of the top and the derivative of the bottom again. You're not going to get the right answer. It's not in indeterminate form. In fact, it's our answer, 8/10 or 4/5, which we knew initially because the degree and top and bottom are the same, so it's just the ratio of the coefficients, 4/5. Okay, so neither of these types of limits you should apply L'Hopitals. Just you can look at it and know that it's going to be 3/7 and 4/5. However, if we had like sine x over x as x goes to 0 this time, we spent, I don't know, 35, 40 minutes one day proving that the limit of sine x over x as x goes to 0 is 1. Remember, it's this graph, and then there's a removable discontinuity, and we evaluate a lot of limits knowing that just sine x over x as x goes to 0 is 1. but we analytically spent a long time doing it. Actually used the sandwich theorem to prove it. This is an example where if you just applied L'Hopital's 0 over 0, which is an indeterminate form, and it's written as a fraction. Derivative of the top is cosine x. The derivative of the bottom is 1. And now we can plug 0 in for x. Cosine of 0 is 1. So we get 1 over 1, which is 1, using L'Hopital's. Same sort of same type of a problem if I had like sine of 2x over 4x as x goes to 0. The old way would be, well, sine of 2x, that's Carl 2 sine x cosine x. That's a double angle formula for sine. And then we were searching out sine x over x's. Well, there's one right there. So that's the same as 2/4 times sine x over x times cosine x. Then we said that's 1/2. This we know is 1 as x goes to 0. Cosine of 0 is 1, so we end up getting 1/2. Okay, so that's the old way of doing it. New way, L'Hopital's. 0 over 0, apply it. Derivative of the top is cosine of 2x times 2. Derivative of the bottom is 4. And you can plug 0 in. Cosine of 0 is 1, so 2 over 4, which is 1/2, just using L'Hopital's. Okay, so like I said before, there's a number of different examples, more involved, but I think just knowing that you can always do the derivative of the top over the derivative of the bottom, assuming it's in indeterminate form and it's written as a fraction, it's a really good way of evaluating limits.